Thank you very much, and it's a pleasure to have the opportunity to give this lecture here in the National Library in Latvia. Can you all hear properly? Yes? So I'll be talking about light rays and black holes, or if you wish, about the physics of black holes. So Einstein's theory of gravity, which was his greatest achievement, is called the theory of general relativity. It was completed just about almost 101 years ago, in November 1915. Of course, Europe was burning, and Einstein, who was living in Berlin at the time, and never supported the war, in fact, he very vocally opposed the war, had plenty of time to work on his theories. Meanwhile, Karl Schwarzschild, aged 41, was a very distinguished astronomer and physicist. He considered it his duty to volunteer for military service. This is a picture of Schwarzschild. Schwarzschild was one of the few people with the background to understand Einstein's new equations. And he worked on the new theory while serving at the Russian front. Just a few weeks after Einstein published his equations, Schwarzschild found what we now understand as the first black hole solution of Einstein's theory. Einstein didn't find that solution himself because he assumed it was too difficult. Einstein did an approximate calculation, which was good enough to describe the solar system to a very high precision, but Schwarzschild found the exact solution, and although it took a long time to be appreciated, this exact solution gave birth to the concept of the black hole. Schwarzschild's paper describing the first black hole was actually published early in 1916, so in a sense, the current year of 2016 is the centennial of the black hole. Einstein was very enthusiastic about Schwarzschild's discovery, writing about it as follows. I've read your paper with utmost interest. I had not expected one could formulate the exact solution in such a simple way. I like very much your mathematical treatment. Next Thursday, I shall present the work in the Academy with a few words of explanation. Schwarzschild died a few months later of a disease he contracted at the front. So we could think of Karl Schwarzschild's life as representing both what was great and what was awful about 20th century Europe, discovering the black hole and dying of a disease he contracted at the Russian front. By the way, I wanted to know what it was meant that Schwarzschild was at the Russian front. Where exactly was he at the Russian front? My mother's mother, meanwhile, was in Poland in an area that was occupied by German forces during the war, so I wondered if maybe Schwarzschild was near where my mother's mother was living. My father's mother escaped the war. She was living in Riga, actually, working as a home servant in the years before the war, but she had the good luck to be able to emigrate to the US in 1909 with her family. Karl Schwarzschild's son, Martin, was born in 1912 and luckily left Germany before the Second War. He became a very distinguished astronomer, best known for his work on the structure of stars. He actually was a professor in Princeton when I came as a student, and later on joined the faculty, so I knew him fairly well. Although when I looked for a picture, I found I couldn't really recognize it, because it was a younger Martin Schwarzschild than I remembered. Now, apart from this year being the centennial of the black hole, it's also the year that the first really direct proof of the existence of black holes was obtained. So this happened with the first direct observation at the LIGO laboratory in the United States of one of the most central phenomena that Einstein predicted, which are gravitational waves. So I'll be trying to explain this more throughout this talk, but you've probably already read or heard at least a little bit that what was observed was a gravitational wave signal from a pair of black holes that spiraled inward and then merged. So I'll be telling you more about this event, but I'll use it as an entree to tell you a little bit about black holes and relativistic gravity more generally. And perhaps if time permits, I'll then conclude by telling you a little bit about what it means for me and my work. So we're going to watch a few movies. And the first movie, well, we'll start with a movie that shows what the LIGO event would have looked like if you were a few thousand miles away. So actually, the LIGO event was 1 billion light years away. We couldn't see it through an ordinary optical telescope. But here we'll see a movie that will show what you would see if you could see it from a distance of just a few thousand kilometers. And we'll look at the movie once, and then we'll talk about it some more and look at it again. So you see the two black holes spiraling around each other. And behind them, you see the more distant stars. Obviously, as the black holes move around, the image of the stars you see behind them is changing rapidly in a way that looks a little bit crazy when you see it the first time. It's as if the stars were jelly and the black holes were turning it around. Now the two black holes are merging into one. And so in the end, there's a single black hole. And this is this slide shows the nice people who made this movie, who also are basically the people who made my other movies. So if you missed something, never mind, because we'll be watching that movie again in a few minutes. So one thing you may have noticed is that the black holes do look like black holes in space. That's because a black hole blocks light coming from behind. So here's a star. Here's schematically, this is an eye. You're trying to look at the star. But the light ray that would come directly to you from the star is blocked. It falls into the black hole and doesn't reemerge. So basically, that's why the black hole looks like a hole in space that light doesn't come from. But it doesn't mean that we can't see a star that's behind the black hole. We do see a star that's behind the black hole because of the way light is bent by the gravitational field of the black hole. So we're here, the star is here. We don't see the ray that would come directly to us, but we do see a ray that goes around the black hole. But this bending means that the apparent position of the star will not be where it really is. The star is really here. The light is traveling to us in a curved path. It looks to us like the star was up here. So that's why as the black holes move around, the stars behind them appear to be moving. I've explained this as if we see just one image of any star, but actually we will see multiple images of the same star. So this is most obvious if the star is symmetrically placed. There's a ray that goes above the star and gets to us. There's a ray that goes below the star and gets to us. But if you think about it a little bit, you'll see that if there's axial symmetry, if you have a black hole that's invariant under rotations, we're on one side and the star is on the other side, a ray could reach us from the black hole above or below, as drawn here, but also in front or behind or in any direction. So actually, the star that's directly behind the black hole will look like a ring on the sky. This is what I just said. With a little imagination, you may be able to see that if the star is symmetrically placed behind the black hole, we'll see a ring, which is known as an Einstein ring. So we don't yet have photos of black holes showing how they bend light, because the black holes that we've discovered are much too far away for us to have such a picture. There's a chance of getting such a picture with a future satellite that might be able to image very close to the black hole at the center of the Milky Way. But for now, we don't have such pictures with black holes. But with galaxies serving as the lensing objects, we do have pictures of almost perfect Einstein rings, showing what it looks like if you're looking at a star which is behind some other mass. The mass that produces the Einstein ring does not really have to be a black hole. So here's an almost perfect Einstein ring that was observed by the Sloan Digital Sky Survey. So what we're seeing is the following. In the front is a massive galaxy, which is this. The blue ring is really not a ring at all. It's actually a much more distant galaxy, a galaxy much more distant than this one, that happens to be almost perfectly placed behind the foreground galaxy, so that what we see is almost a perfect Einstein ring. So this ring is made of an object that if light were not bent by gravity, would a galaxy just behind this one and much more distant and faint? But because it's almost perfectly placed behind the nearby galaxy, and the more nearby galaxy is almost point-like, we see an almost perfect Einstein ring as the image of the blue galaxy. Now, this is a chance coincidence that gave an almost perfect Einstein ring. What we typically see is less perfect, so I'll also show you a more typical picture. This is a more typical picture from the Hubble Space Telescope. So the gold objects in the foreground are a cluster of bright galaxies. They're lensing more distant galaxies, producing arcs. So you see a lot of arcs in the picture. Here's one, here's another, here's another. The arcs are pieces of Einstein rings. In these cases, we only see a piece of an Einstein ring because the object which is being imaged is a little bit off-center. So a Hubble deep field photo will typically show us these pieces of Einstein rings, and when you get very lucky, you see an almost perfect Einstein ring. Now we're going to look at the movie one more time, but we'll talk about it a little bit first. So the two black holes at the beginning are orbiting each other, a little like the Earth orbiting the Sun. But as they accelerate around each other, they emit gravitational radiation, which is ultimately the radiation that was observed by the LIGO experiment, as we'll discuss later. Emitting radiation causes them to lose energy, and as they lose energy, they fall in closer to each other, which also makes them speed up and move around each other faster. Somewhat like the planet Mercury, because it's closer to the Sun, moves around the Sun faster than the Earth. As the two black holes spiral inward, they also start moving faster and faster. When they get too close, they merge into a single black hole. And I think it's amazing how quickly that merger happens. The process is speeding up, speeding up, speeding up, and then suddenly it ends, and very, very suddenly, everything is calm and there's just a single black hole. Then finally, as we've already discussed, as the black holes move around, the star field behind them is greatly distorted by the bending of light by the black holes. So here's the movie again. So the black holes are orbiting and distorting the star field behind them and gradually creeping in closer because they're losing energy to gravitational waves. We'll see other movies where we see the waves better. Then they start to orbit closer and faster, and they're going to merge, and then very suddenly it's all over. So the suddenness with which it's all over actually came as a surprise, but it was discovered by computer calculations that were done just in the decade before the observational discovery. We're lucky that the computer work advanced fast enough to show that before the LIGO observation was made, or the observation would have been a mystery. Now, why is light deflected by gravity? In other words, why does the black hole bend a light ray that's coming from nearby? Actually, Einstein guessed this even before he invented his theory. He knew that a comet or a planet is deflected by gravity, so he thought it would happen for light. So since Newton's day, scientists had known that the deflection of an ordinary body, such as a comet by the sun, depends only on its velocity, not on its mass or its composition. So here's a slow body being deflected by the sun. It spends a lot of time passing by the sun, and it's deflected a lot. A faster body passing by the sun speeds by rapidly and is only deflected a little bit. So Einstein took the classical formula that goes back to Newton and guessed that the same effect would hold for light. He simply used the speed of light in Newton's formula for how much a body is deflected by the sun. The effect was so small it could only be observed during a total eclipse of the sun. The angle by which Einstein said that a light ray would be deflected was such that if a star was passing just behind the sun, it would be deflected by an amount that would be just barely measurable with the best telescopes of the time, except for one catch. The sun is so bright that you can't see the stars when they're near the sun. So you have to go to a total eclipse of the sun when the sunlight is blocked out. Then you can see stars that are quite close to the sun. And Einstein predicted, in fact, that was supposed to be just barely observable. Well, at this point, Einstein got lucky, though at first his good luck looked like bad luck. An attempt to test his idea was made at an eclipse in Brazil in 1912, but it was rained out. Nothing was visible because it was cloudy. And another attempt in Russia in 1914 was thwarted by the outbreak of World War I. In fact, the astronomers with their measuring equipment were suspected of being spies and were lucky enough to not be thrown in prison and to get back safely, but without their data. So this looked like bad luck. But during the war, Einstein finally developed his theory, general relativity, and it became clear that the Newtonian formula was 2 times too small. Luckily, his original prediction had not been tested. So his proposal had not been disproved because of the bad luck in 1912 and 1914. Finally, after the war, science resumed, and the eclipse expedition of 1919 confirmed Einstein's prediction. This actually was the event that made Einstein a household name. Here's how the event was reported in the New York Times, for example. I imagine there were similar headlines here in Latvia. Light all askew in the heavens. Men of science more or less agog over results of eclipse observations. Einstein theory triumphs. Stars not where they seemed or were calculated to be, but nobody need worry. A book for 12 wise men. No more in all the world could comprehend it, said Einstein when his daring publishers accepted it. His daring publishers, I guess, being the publishers of the proceedings of the Berlin Academy of Sciences. So, that, as I said, that was the event when Einstein's theory was confirmed that made him a household name, and there was a little luck involved because the wrong prediction might have been tested a few years earlier. So Einstein's theory was based on reinterpreting gravity in terms of curvature of space-time caused by mass. So this is a schematic picture that I've taken from Wikipedia that illustrates it very roughly. You imagine the Earth as a mass that bends the space around it, a little bit like a marble sitting on a sheet of rubber would bend it. So that's a good picture up to a certain point, but it misses something, which is that what, according to Einstein, is bent is space-time, not just space. But unfortunately, although we can draw space, we really can't draw space-time. So this is the best picture I can offer, but in your mind's eye, if you can imagine it, you have to imagine that space-time and not just space is bent. Now, imagine the moon going around the Earth. Newton said that the moon is attracted toward the Earth and therefore goes around it in an elliptical orbit. Einstein's interpretation was that the moon is seeking the straightest path in a curved space-time. And that straightest path happens to be the ellipse. So to properly describe it involves the mathematics of curved space-time, but a simple picture is to imagine a marble that's moving on the curved sheet of rubber bent by the Earth. Well, it wouldn't go in a straight line. It would actually tend to go in an elliptical orbit around the central mass. So that's as good an explanation as you can get without describing it properly with the curvature of space-time and not just of space. So now when we think about a black hole, we should think of a highly curved region of space-time. So now I'm going to show another movie of the LIGO event, which tries to help us visualize how space-time is curved, as opposed to showing us what we would see if we were there, which is what the first movie showed. And this next movie will also show a couple other things the first movie didn't show. It'll show us the time before the final event, and also it'll show us the strength of the gravitational wave signal. So the movie starts at 0.76 seconds before the final event. And the wiggly line at the bottom will be the gravitational wave signal. And LIGO was only sensitive enough to see the last 7 wave fronts. So it's this part at the end that LIGO saw. But the movie begins earlier. And these black dots are the black holes. We're going to zoom in on them in a moment as soon as the movie starts. And also, the outgoing gravitational waves are depicted like so. They are ripples in the curvature of space-time. So there are black dots, which will be much bigger when the movie is played and we zoom in. And they tell you where the black holes are, but they're just drawn there to draw the eye. What you really should look at is that underneath those black dots, there's a dip in space. That's the hole in space that's created by the black hole. What the black hole really is to me, I'm afraid I have to start the movie so I can show it to you. The black hole is really this hole here, not that black thing up above that was drawn to tell you where to look. These are the black holes. The highly curved regions in space are the black holes. We're 0.44 seconds before the final merger. The black holes are these dips in space, not those balls that were put there above. And we're getting closer, so the black holes are getting closer, and the curvature of space is going to get even more extreme. The movie will also be stopped at a certain point. So the black holes are merging. You can see that the 2 dips in space are combining into one. We're 0.007 seconds before the final merger. They're kind enough to stop the movie here. And now there's just one black hole left. And you can see the outward ripples. Now they zoom out to show you the outward ripples of gravitational waves. So I think I could have explained it a little bit better if I'd remembered how to stop the movie in the middle. So at the end of the movie, we saw the outgoing ripples that represent the gravitational waves. So what are gravitational waves? Well, if I move an ore in the water, I create water waves. If I take an electrically charged body and shake it, for example, if this is electrically charged and I shake it, I'll create electromagnetic waves, which become radio waves or light waves, waves of visible light, if the shaking is fast enough. According to Einstein, if I shake a mass, I create gravitational waves. And it was clear from day one that this was one of the most basic predictions of Einstein's theory, that whenever a mass is not moving in a straight line, it's emitting gravitational waves. But Einstein and his contemporaries thought that this part of his theory would never be tested because gravitational waves interact so weakly. So why did Einstein think that gravitational waves could never be observed? Well, there are 2 reasons. First, he did not anticipate the modern technology that made LIGO possible. So technology developed much faster and much farther than Einstein imagined. But Einstein and his contemporaries also did not imagine such powerful sources of gravitational waves as the merger of 2 black holes. So even though Schwarzschild had published his solution just before his death in 1916, it was a long time before it was understood what the solution really meant, and it was not until relatively modern times that it was understood that black holes are real objects in the sky. So Einstein simply did not imagine any source of gravitational waves that was nearly as powerful as the event that was actually seen by LIGO. Now I'm going to show another movie that emphasizes the gravitational waves that come out of the LIGO event. So in this movie, the black holes are just shown as black dots. They don't, not dots, black disks. They don't really try to show the curvature of space, but they emphasize the gravitational waves. Okay. I'm not sure. I hope the next movie is going to work. So this was a very nice movie. that shows two black holes spiraling around, and it shows the waves propagating outward, that in the end are a little bit like the ripples you see in a pond. If you throw a stone into a pond, you'll see ripples going outward. Here, there are the two black holes going around each other, and as they spiral in, there are very strong ripples going out. Well, how strong was the gravitational wave created by this event? Well, this symbol here represents the sun to astronomers, a circle with a little disk inside it. Actually, that symbol is much older than modern astronomy. It was an astrological symbol for the sun in centuries past. So this represents the mass of the sun. M with this symbol is the way astronomers write the mass of the sun. I don't think astrologers worried about the mass of the sun because they didn't understand the sun as a physical object. The black holes that merged in the LIGO event had masses of about 29 solar masses and 36 solar masses, but the final black hole had a mass of about 62 solar masses. So with a little arithmetic, you'll see that a mass of 3 solar masses disappeared. What that actually means is that that amount of mass was converted into gravitational waves. And because E equals mc squared, the energy in the gravitational waves was 3 times mc squared. So that's vastly more powerful than any source of gravitational waves that Einstein imagined. Now, this event happened about 1 billion light years from Earth, so it arrived at Earth 1 billion years later. And if the movie works, we'll see a cartoon of what happened when the gravitational wave reached the Earth. This cartoon is so much exaggerated that it makes physicists laugh. Maybe you will laugh too. But then again, maybe we won't be able to see it. I guess we'll have to skip this movie for now. So finally, the ripples in space-time that were created by this event traveled through space for 1 billion years and finally arrived at Earth, where they created ripples in the Earth that we're not going to see exaggerated by that movie, and they were detected by the LIGO detector. The LIGO detector is actually 2 facilities. One is in Washington State and one is in Louisiana. The one in Louisiana is in a dense forest, and the one in Washington State is in a desert that you see here. And the facility consists of 2 arms, each a few kilometers long, this way and this way. Laser light is bouncing up and down here. It's bouncing up and down here. When the signal reaches the point where the 2 arms meet in the center, there's a sort of half-silvered mirror that can let some of the light through. So a photon coming this way or coming this way might go through the mirror and be detected. But it's arranged so that if the 2 arms have precisely the same length, the 2 waves will interfere and nothing will be observed. A passing gravitational wave will slightly change the length of this arm or slightly change the length of this arm, depending on which way the wave is going and how it's polarized. And by slightly changing the length of one arm relative to the other, it will create a signal that's observed in the detector. So that's how LIGO actually sees the gravitational wave. The strength of the gravitational wave was such as to change all lengths on Earth by about 1 part in 10 to the 20. So the radius of the Earth is something like 10 to the 10 centimeters, 10 to the 9 centimeters. So the whole radius of the Earth changed by 10 to the minus 11 centimeters, which we really don't notice. It creates an unobservable vibration of the whole Earth that was an exaggerated version of which was in a movie I didn't show you. The arms here are a few kilometers long, so they change in length by something like 10 to the minus 14 centimeters. So the LIGO instrument was so sensitive that it detected a change in the length of this arm relative to this one by perhaps 10 to the minus 14 centimeters. That's possible because of the interference pattern between the laser waves bouncing this way or bouncing this way, which is affected by the gravitational wave. So here's the actual data from the facility in Washington State. So The height gives the amount by which the one arm is stretched relative to the other. And at the beginning, this is just noise, actually. The noise level is about 0.3. So noise means that there are all kinds of other things that could affect what's being observed, such as seismic noise from the Earth. The reason they have two detectors is that to distinguish a real signal from seismic signal, one important technique is to see the same thing at the two detectors. So after being displaced by 7 milliseconds, the gravitational wave traveled at the speed of light and arrived at one detector 7 milliseconds before it arrived at the other detector. After being displaced by 7 milliseconds, so the blue is the signal at the second detector. It's being compared to the red from the first detector after displacing one by another 7 milliseconds so that they match. You can see that during this period they match very well. At the beginning, when it's noise dominated, they're not matching. But for about 7 peaks of the wave, they match very well. Down here is a theoretical calculation based on a computer simulation of the event based on Einstein's theory. And because the two detectors are slightly oriented differently, there are different simulations for the two detectors, but you see they both match the observed signals very well. So this is the data on which the first decisive confirmation of Einstein, on which the first direct observation of Einstein's gravitational waves was made, and the first really decisive observation of a black hole. Now, there's something else about how light interacts with a black hole that you probably know, but that I haven't explained, so I'll explain it now. And here we're going to take another look. So space runs horizontally, time runs vertically. And so the black hole is just a black hole in space that's there for all time. So I've drawn it as a cylinder in this space-time picture. And now I'm going to draw a light ray in such a picture as moving at a 45-degree angle, representing the speed of light in space and time. So in the absence of gravity, a light ray is represented by a 45-degree angle. Here's a light ray escaping from the black hole. When it's near the black hole, it moves slowly, which means in the picture it goes almost vertically. But as it escapes, it eventually will go at a 45-degree angle. But if it's closer, it has more trouble escape and will be nearly vertical for longer, but eventually it escapes. But as it gets closer and closer, it has more and more trouble escape. Finally, a light ray grazing the horizon of the black hole, grazing the surface of the black hole, doesn't escape. It stays there forever. And from the interior of the black hole, not even light can escape. Now, I'm hoping to conclude with one more movie, but we'll see if it works. It's a movie that shows what happens if a black hole passes in front of a galaxy. So in the starting point, which at least I can show you, here's the galaxy, here's the black hole. You see a ring of fire around the black hole. What the ring of fire means is that some of the light from the galaxy is bent near the black hole and scattered toward us. So the black hole without the galaxy would just be black. But even though it's far away from the galaxy, some light from the galaxy is scattered toward us. Okay? And this movie repeats, I think. So I'll get the chance to explain it again. So, okay, the black hole is approaching the galaxy, and it'll greatly distort what we see behind us in the galaxy as it goes through. And you see also the ring of fire gets very complicated. As it passes, we see again the ring of fire surrounding the black hole. The only trouble is that if something like this happened, it would take 500,000 years or so. It's been compressed into a few seconds, but you wouldn't be able to take a real movie of this because it would take a little bit too long. And I think maybe we won't press our luck with the other two movies. We'll stop there. Although it's tempting, but probably will lead to more disappointments. Okay. So we'll stop here for questions.
I'm wondering if we have questions. in the audience. There's a question.
Fantastic. I have a question. You use in your presentation the present tense.
Yes.
But the things reflect something which happened billions of years ago.
Yes.
Seeing those black holes merging together,
Yes.
my question would be, are there so many black holes out there that they merge into one and nothing is left? We are just alone, desperate.
Well,
Can you console me in this nightmare?
sorry, there are different parts of the question. I'll respond to some bits, but if I missed your question, you can ask a follow-up. So first of all, there seem to be a lot of black holes out there, but we have different ways of observing them, none of which is as direct as what LIGO saw. But the LIGO event was actually a surprise. I'm afraid I didn't explain this in my talk. Nobody knew how common binary black holes were. And you couldn't be at all sure that you'd ever see a pair of black holes spiraling in. It was a dream because the LIGO team knew that that would be their best source, but they saw such an event 5 days after they turned on the new detector. But for all we knew, it could have taken 500 years before they would have seen one. We really didn't know. So we know there are a lot of black holes up there, but we don't know how many there are. And the LIGO event kind of was a surprise. We certainly didn't know that there were binary black holes. I don't think astronomers understand very well how the black holes in the first LIGO event, the one I showed you, are in a mass range that's a little bit embarrassing for astronomers. They don't even know how to make 30 solar mass black holes very well. So there's a lot about this. Anyway, there's a lot about black holes that we just don't know. So LIGO, we at least are now going to be able to have a solid way to determine how many binary black holes there are, because we can observe them due to their gravitational waves. If a black hole is just sitting there in empty space, there's not much matter nearby falling in, and we're not lucky to see it as a gravitational lens, we probably don't know about it. So it's pretty hard to know how many black holes there are. I'm not sure if I answered the question or not.
The point is the tense.
Yes.
You use the present tense, there are, they are.
Yes, okay. Right.
My point was they were.
Okay.
And the fact that I wanted to be consoled about is, can I believe that something exists beyond our solar system?
Well, the LIGO event happened roughly 1 billion years ago. But 1 billion years, even though it's a very long time on a human scale, is not long compared to the evolution of the universe. So any type of event in the universe that was happening 1 billion years ago is still happening today. So there are certainly events like this still happening. But if it happens 1 billion years from now, sorry, if it's happening now 1 billion light years away, we'll have to wait 1 billion years before we see it. But we can be pretty sure that similar events are still happening.
Any other questions? Let's make a quick survey here. Please raise your hands who understood this. That's quite many.
Everyone understood it.
Come on.
Everyone understood it.
It's kind of wishful thinking in a way. Please raise your hands who kind of understood what he was talking about.
I'm glad to see that most were in the first group.
Yeah, it's a decent result. Thank you for that. Mr. Witten, thank you for coming and yeah, awesome.